We just heard a beautiful talk by Kosterlitz about how they came up with their idea of the vortex unbinding. In fact, I want to tell you a few things that happened after they published the paper, which is when I started to do physics. Of course, everybody has seen this picture now. You may be too familiarized with seeing yourself all the time. Of course, David is not here. We just have Duncan Haldane and Mike Kosterlitz. And as I mentioned before, this morning, we were actually quite happy that we actually put together this book in 2013. As I mentioned before, there is a very nice review article that was written by David Thowles and Mike Kosterlitz that I recommend you to read because it has a lot of the background stories, some of the ones that he mentioned today. Let me again say that this was a very good idea from Professor Pua to try to put together a volume that will review some work related to the Kosterlitz-Thowles, Brzezinski-Kosterlitz-Thowles theory. In this review article that Mike Kosterlitz and David Thowles wrote, they actually mentioned the importance of work that was done by Phil Anderson, Yuval and Hammond's work. And in fact, the history about how David Thowles was visiting Stony Brook, and then he went to visit Phil Anderson at Bell Labs. And Phil Anderson actually asked him some questions that led him to start thinking about the problem that led to the work of the Kosterlitz-Thowles transition. Now, the importance was, one of the things that was very important is that they were studying the Kondo problem. The Kondo problem, one of the representations for the Kondo problem was a one-dimensional Ising model with 1/r square interaction that in fact leads to a model that is a two-dimensional Coulomb gas model. This Kondo problem is a quantum problem, so this is a 1 plus 1 dimensional representation of that problem. And in fact, the scaling equations, the renormalization group equations that Mike Kosterlitz derived were induced, if you wish, motivated by the scaling equations that were done by Hammond and Anderson and company. I must say that the first paper that Anderson and company published was 1969. The paper by Ken Wilson actually was probably 1971. So I want to now connect, in fact, to some of the questions that were just asked recently. So we heard of all the heuristic arguments that were put together by Mike Kosterlitz and David Thowles. I mean, the energy of those vortex excitations that could be in a two-dimensional system. The fact that they did this quadratic approximation that neglected the quartic contributions of the expansion. If you consider an XY model representation of the two-dimensional superfluid helium problem. And of course, the central idea that they consider the existence of these bound vortex pairs at low temperatures and the fact that they could unbind as you raise the temperature, and that led to many of the results that they found. So, but in fact, the response to the paper, and of course, partly maybe it was not published in History of Letters, but also there were some people working on this problem that were not convinced about the separation of the spin waves from the vortex excitation, because apparently they assumed that they had neglected some interactions that could be important to change the criticality properties of the problem. And in fact, there was a paper by Alan Luther and Doug Scalapino where they used some exact mappings of quantum systems. At that time was popular, still today popular, trying to go into bosonization, in which they calculated the critical exponents that would correspond to the two-dimensional representation, the 1+1 quantum representation of a two-dimensional problem. And in fact, they found very different types of results. They found different exponents to the ones that were obtained by the calculations of Kosterlitz and Thowles. There were also some papers where they were trying to, by Johann Sitterts in Germany, when actually he did some self-consistent calculations, and he was not able to get the same results as Kosterlitz and Thouless when they added some extra corrections. And one of the issues, I mean, people were trying to understand better what they had done in more better approximations to the calculations, if you wish. And the reason I'm mentioning these papers is that I was, first I was a graduate student of Leo Kadanoff, and then he hired me as a postdoc. He went on sabbatical in 1975, and he came back and he said, well, we need to figure out what's going on with this problem. I mean, is there really a phase transition or not in this problem? And he had just visited Sitterts in Germany. Of course, Alan Luther was at Harvard next door to us, and Alan Luther came to visit us also when I was at Brown University. And he had also been to the Soviet Union at that time, and he had met Sasha Migdal, and he heard about this renormalization group approach for lattice gauge theories that Sasha Migdal had developed. So in fact, when he came back from his sabbatical, he asked me, well, first of all, he hired me as a postdoc, and he asked me to work on this problem. And there were a number of things that were happening at that time that actually played a role for the work that we did. The first one, of course, was the success of the standard model after here Hooft and Feldman were able to show that the U1, U2 model gauge theory was renormalizable. Soon after, I think that in trying to do strong coupling calculations, Ken Wilson, of course, first developed the renormalization group around 1971, but then he also developed the lattice gauge theories, how to do non-perturbatory calculations in high-energy Lagrangians. More about the same time in the Soviet Union at that time, not Russia, the Soviet Union, there was Sasha Migdal and Sasha Polyakov that were doing calculations of lattice gauge theories for 1 billion O2 and 1 billion O3 models. They actually found some interesting results. One of those, for example, if you look at the 2 plus epsilon dimension calculations, epsilon is a lower critical dimensionality for vector models, and they found that most of the exponents had expressions, 2 plus epsilon type corrections, except for the O2 model, the XY model, they have 2 minus epsilon type results, so it couldn't be applied to the case of the XY model. At the same time, there were developments about topological excitation, solitons, instantons, magnetic monopoles, and so on and so forth were actually being pursued very strongly. And as I said, there was a renormalization group approach to calculation to try to study lattice gauge theories with abelian symmetries. So let me actually show you a picture. Brown University. Mike Kosterlitz wasn't there yet. So here's Leo Kadanoff. There's Leon Cooper, and I must be somewhere around there here. That's when I got to Brown, when I came to Brown for the first time. As you may know, I mean, Leo Kadanoff, another giant of statistical physics, passed away in 2015, and he was my advisor. And just as Mike Kosterlitz said about working with David Thouless, he was intimidating. Leo was very intimidating to work with as well. So one of the things that we decided to do is we decided to study the XY model exactly, to start to do things with the XY model exactly. As you know, there's universality, so because of universality, the only things that matter was the dimension of the other parameter, dimension of the space. So if we defined the spins by the cosine angle, I mean, the ones that was shown by Kosterlitz, and then the interaction of the Hamiltonian is given by this cosine interaction, and you want to calculate the partition function. Of course, we know that nobody has been able to calculate this partition function exactly for 2 dimensions or 3 or any other dimension as it happens in the case of the Ising model in 2 dimensions. So one of the important things that actually was pointed out by Bershinsky and also by other people is that when you do this quadratic approximation of the cosine, and if you just replace the cosine by the square, you are missing a very important symmetry that the cosine has. That is, you can add a 2 pi times an integer, and this is invariant. The cosine will be invariant. And in fact, if you look at the lattice, you can actually change the angle by a 2 pi an integer localized at some lattice site. And in fact, you can actually look at the symmetry also of adding 2 integers. Then the symmetry of the Hamiltonian is actually has a gauge invariance, as you have in quantum mechanics. You have for the phase of the wave function. So one of the things that we wanted to do is we wanted to preserve and to at all times maintain gauge invariance in all of the analyses I wanted to do. And so we started by looking at the Hamiltonian or the action, okay, which is a periodic function of the angle, and as I said, it has some symmetry. So you can immediately realize that if you look at the action, so the potential e to the Hamiltonian, that this function actually has a periodicity symmetry can be expanded in terms of the group property U1 periodic group expansion. Explicitly in the case of the U1 discrete symmetry would be the e to the I nu theta, where these nu are those integers that I mentioned before. So you can expand the e to the Hamiltonian in the case of the partition function, and then you will get a functional expression in terms of an expansion in terms of the characters of the U1 group representation of the U1 symmetry. If you do that, then what you have is that the partition function for a certain lattice geometry can actually be written down as just an integral over this function that is periodic in terms of this adding this integer 2 pi times an integer defined in the lattice. So the whole lattice, every 2 points in the lattice, we are going to have this thing being satisfied. Now, if you use some identities, and I'm not going to go through the details here, the Poisson identity to try to represent the expression that we have here when you have the interaction that appears here in terms of some Bessel function, you can immediately define a variable, which is going to be, let me call it an n variable, which is going to be an integer circulation around the plaquette of a lattice. And in fact, you can represent the partition function exactly as the sum over these integers, which are going to be circulations about the plaquettes, about the lattice circulation of the exponential of the sum of some interaction that is modified because of the transformation by this representation in terms of the expansion, in terms of the characters. But the very important thing here is that we have 2 representations of the problem. One is a representation in terms of the angle variables, and the other one is a representation in terms of these integer variables, which of course are going to be the vortices. Now, this transformation, which I think that we were the first ones that wrote this transformation, corresponds to something called a duality transformation in statistical physics. And what that means is that the partition function can be represented in 2 different representations, one in terms of one variable here, which are the vortices, the other one which is represented by theta, the ones that represent the spin wave type oscillations. Now, this duality transformation is exact. It's absolutely exact. No approximations made. It's exact. And this is important, and I'll tell you why it was very important. Because after we started from here and went beyond, then people realized after we actually re-derived exactly the same results as Kosterlitz and Thouless, but exactly. We did the things exactly, no approximations. Okay. So what we have is then again you have the spin wave dual to the vortex duality, which means that we can relate the strong coupling region of the partition function of the Hamiltonian being dual to the weak coupling. So the spin waves are actually dual to the particles or to the vortices. I'm sorry, the vortices are dual to the spin waves by this duality transformation. I will mention at the end that in fact these duality transformations are very hot in physics, theoretical physics today. They are being applied to everything. Okay, and as far as I know, except for the duality transformation that was developed by Kramers and Wannier, that was self-dual for the IC model, these types of dualities just started to appear after we did this thing. And there were other things that came afterwards that is called the Hove-Mandelstam. I mean, there are many other types of dualities. But the important thing about this thing is that you can relate strong coupling to weak coupling and learn lots of things about the two sides of the problem without having to do explicitly calculations. Oops, this thing is just... So again, this is what was happening. And now, as I told you, when Leo came back to Brown, he had this, he was very excited about this Migdal renormalization group transformation. So the first thing that he said, okay, now we have this duality transformation. Let's do Migdal type transformations for the exact version of the XY model. So this Migdal type transformation actually is called a decimation transformation. You transform a problem that is in 2 dimensions to actually 1-dimensional problem. And so we started with, we want to do renormalization group transformations. We want to transform the Hamiltonian by doing scaling transformations, starting from the exact Hamiltonian. Okay, so we have that the partition function originally is just this k, the coupling constant, times the cosine of the interaction between the two things. We can do it in the spin wave or angle representation, or we can do it in the vortex representation. The renormalization group equation, this is the exact renormalization group equation in the Migdal approximation in terms of decimation, is very simple. Z prime is the new partition function. Z is the original partition function. The decimation transformation means you sum over the intermediate variables, taking the square in 2 dimensions of each one of these partition functions. The remarkable thing that we found is that as you do this, in fact, we did it analytically first, and then we did it numerically in detail. The remarkable thing was that after you did this transformation many, many, many times, you ended up with an action, or with a Hamiltonian, that was a theta minus 2 pi n square. It's like if you had expanded the square, maintaining the gauge invariance in the expansion like this. So the fact that that became a fixed point Hamiltonian led us to consider now an analysis in terms of a Hamiltonian that is going to look like this, which in fact had been already thought about by Villane in France before. Okay? But the difference in what Villane did is that we arrived at this as a fixed point Hamiltonian, not as an approximation as Villane did in his papers. Okay? And it's exact. There are no approximations. We did this analysis of the Migdal-Kadanoff approximation analytically, and we got this result. This is the beta function for the renormalization group transformation that gave us equations that look like this: e to the minus 2/3 pi squared k. This is like the fugacity that you were looking at before, times 8 pi squared. Now, in this expression that we have here, we don't have this 2 minus pi k that you found in the renormalization group equations originally. So we had this question. In fact, I remember it was very depressing because on Monday, Wednesday, and Friday, Leo said there is no transition in the XY model. There cannot be. And on Tuesdays and Wednesdays, oh, there has to be a transition. Okay? It was so, in quotation mark, depressing that I disappeared for 3 months. I didn't want to see him for 3 months. I just wanted to go and do my own thing because we didn't know what was going on. The numerical calculation was being done by Scott Kirkpatrick and in collaboration with David Nelson. when they were at Harvard. Okay, so what we then decided to do is, now that we had this result from the renormalization group calculation about the asymptotic expression that was going to tell us about what's going on in the model without approximations, okay? So we could actually look at the problem either in the angular representation, spin wave representation, or we could look at the problem in the vortex representation, okay? The vortex representation in terms of a variable phi, in this case, that goes from minus infinity to infinity, with an added variable here that is a multiplication of this vorticity times this variable phi, okay? So we could do it in this way, or we could do it in this way, which we call the generalized Villain model approximation. And here's the remarkable thing, and I just say, what we decided to do is we decided to calculate the correlation, spin-spin correlation function calculations. Now, the original calculations that several people had done, including Vershinsky and Sitars and other people, had this expression. You know, the spin-spin correlation function in our analysis now had the separation between the spin wave and the vortex as you had done, Mike, originally. But of course, the coupling constant that appears here is a renormalized coupling constant. This renormalized coupling constant satisfies this equation here, which is, this is the unrenormalized coupling constant, and then is the sum over the correlation function of the vortex correlation function. So I have a vortex here and I have vortex there, and I want to know how they correlated as a function of temperature. Without going into the details, you know, the remarkable thing is that after we did the scaling analysis, we came back to the same equations that Mike Kosterlitz and David Thaulis had derived before, okay? But now I think we had the foundation and the basis to believe that this was actually correct, completely correct. And in fact, all of those people that were working on this problem, trying to having alternative theories, disappeared, okay? And in fact, it was after, you know, we published this in 1977, and if you look at the citation index for the KT paper, it just went exponentially after that, okay? So very soon, in fact, soon after we wrote this paper, I think Mike Kosterlitz and David Nelson actually used the results that they had done before to derive this expression, this universality expression that he just mentioned in terms of the experimental results that were done by John Reppe, which are given just in terms of basic fundamental constants of physics, okay? And the fact that they were, and of course John Reppe will tell you, I mean, they had looked at this thing before, and it was very quickly that they actually had the paper published because they had the data. They had done the experiment, and it's just how do you fit the data is what they hadn't done. So soon after, well, after we found this thing, we wanted to generalize the problem that we started with, you know, this cosine interaction. And one of the reasons is, as Mike Kosterlitz said, is that in real systems, substrate, you're looking at two-dimensional system. Two-dimensional systems usually are sitting on something. And that something is going to perturb completely the symmetry of the Hamiltonian, and it may affect the results that you're going to get from the Hamiltonian. So we wanted to consider an extra contribution to the Hamiltonian, which is symmetry breaking fields, fields that are going to break the symmetry. How important are those symmetries going to be broken is going to depend on this parameter that appears here, this p parameter, which is an integer, that can tell you if you have Ising symmetry, you have a three-fold symmetry, a four-fold symmetry, and so on and so forth. Following the same logic and the same analysis as we follow for just the regular XY model, we derive new duality transformations for this generalized Hamiltonian, and we found new renormalization group equations. In particular, we found that the partition function was dual to this partition function that depends on p squared over 2 pi k in the denominator. Remember, k is 1 over temperature. Yp is the thing that controls the excitations due to the symmetry breaking field, and Y0 is the thing that controls the vortex excitations that appear in the Hamiltonian originally, depending on the number of spins that you have there. And you have these renormalization group equations that in fact give a phase diagram that tells you that you're going to have a phase transition of the KT type or not KT type, depending on the value of P. That we can see in this phase diagram, in particular for the case of the six-fold symmetry breaking. Six-fold is important. It was important for some experiments. So what you have in this phase diagram is, below this point here, you have a line of fixed points, the KT line of fixed points. Above this critical temperature, that critical temperature is given by this bound that I gave you. You have all of these things that also will have power law correlation function behavior, and at high temperature you have exponentially dependent behavior. There is a particular value of 4, symmetry 4, where you have just a line that separates the high temperature from the low temperature, depending on the value of this symmetry breaking field. Now, this type of problem is still very active. I mean, Gerardo Ortiz has written papers, I don't know, some papers about this. The number of questions still about this is not as well understood as in the case of the regular XY model. So this, all of this thing I just mentioned to you was published together with Scott Kirkpatrick and David Nelson and Leo Kadanoff many years ago. But soon after this paper was published, then Leo Kadanoff and others and myself too were able to show that this two-dimensional XY model represented in terms of the Coulomb gas interactions actually is related to a Baxter model. Baxter model is something that was solved exactly. Is related to the F model, the ice model, the solid model. There's a whole family of models that fit into exactly this thing, okay? And all of this thing leads to, again, to some kind of KT type correlation results to the critical properties of this problem. Now, a year or two later, there was actually about the same time, 1 year later, there was Mike Pesking. There was a student of Ken Wilson, and we talked a lot. He was at Cornell, he was doing his PhD, and then he went to Harvard as a postdoc. And he expanded this idea of the duality transformations and generalized type VLAN models to gauge theories, periodic gauge theories in 3 dimensions and 4 dimensions. Dasgupta and Halperin also extended this a little bit later. And look at the Hamiltonian, look at the partition function that they have here. So here you have what you would get from generalized VLAN model, but you add a vector potential for an electromagnetic field to the Hamiltonian, square. And this is the product F mu nu that you usually have there. You can look at this problem in terms now of 2 variables. One is the K, one over temperature, but the other one is the charge. The charge that appears multiplying here the vector potential. This model is self-dual. Okay, the charge and the temperature are self-dual to each other. This model is cited a lot today because this is a self-dual model. It's a duality-related model that's being applied a lot to in things that relate to high-energy superstring theory and so on and so forth. This model was actually one of the first models that was developed as an extension of what we were doing. So, and one of the things I wanted to emphasize, one of the things that came out of our analysis was the development or the discovery of this duality transformation in the XY model. But that duality transformation actually is ubiquitous in physics. Okay, it appears all over in physics now. In fact, I was looking at a talk that Nathan Seberg gave at Santa Barbara, and he gives all of these kind of dualities: boson, 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 fermion, fermion, fermion. People are finding a whole family of transformations that are directly related, to the ones I just mentioned, to adding different types of Chern-Simons terms to the Hamiltonian. And this thing just expands completely the application and applicability of all these ideas that we started to develop in condensed matter physics. But in fact, we can say that there is quite a unity or a ubiquity in physics about the ideas we develop in one field and we end up applying in another field. Okay. In fact, there are lots of applications of the KT, VKT type theory in confinement. People that do experiments in Stony Brook and all that, they apply a lot of the same type things. So the conclusion is that it was incredible that this seminal idea that KT had, and also Bershinsky had, about these individual excitations, vortex excitations in 2 dimensions, they can generate a phase transition that doesn't have the same structure as the ones that Landau studied, okay? In terms of the fact that you don't need another parameter, in terms of the fact that, in particular in the KT model, it has this essential singularity. There's no perturbation theory in temperature. You have e to the minus BKT for the vortex fugacity, okay? So I'm very happy that we are celebrating that paper here today, I mean that work by Kosterlitz and Topological. And again, I recommend that you read the paper because it's very informative about how they came up with this idea, okay? And thank you very much. Too fast.
Yes. So in the Migdal-Kadanoff RG, so do you get the RG equation which are already weak into the dilute limit, or it was?
So what you get is an exponential decay. You know, in the beta function, it almost fits the. If it was 0, if you had an intercept in the axis, then it would be a phase transition. But it's exponentially close, but not quite. Okay, so that's why we have this question about, is there a transition or not? But it was very useful for us to use the Migdal approximation because we ended up with a VLAN model after many iterations. That's the thing that was non-trivial. That's the thing that was non-trivial. Because otherwise, if we would have used the VLAN model to just justify what Kosterlitz did, people would not have believed that. But the fact that we could prove that there was a fixed point Hamiltonian after many transformations, that was it, I think. Yes, I think. Yes.
You mentioned the duality for different the terms. Here, what are you talking about explicitly? Can you tell
different
us?
Terms?
For the different Chern-Simons terms, you mentioned the duality. You mentioned in your slide the duality is for different the Chern-Simons terms. So what are you talking about here about the?
You mean the Hamiltonian? Or
yeah, the different Chern-Simons terms. What are you pointing out here?
No, that was Seiberg.
Oh,
Seiberg. No. In the Seiberg, in the particle physics, you add this Seiberg Chern-Simons terms, okay, which is just a topological term adding to the Hamiltonian. I mean, that's just the same thing that happens in the Majorana, the same thing that happens in all those things. That's just an extra topological term you add to the Hamiltonian, okay, and then different forms that you can add depending on the symmetries. Yes, yes.
So when you are calculating the partition functions for the vortex representation, you summarize over a integer parameter. What?
Some.
Yeah. What is the integer parameter n represent?
It represents the vorticity. In fact, the n, I was too fast because one variable is n, the other one variable is m.
Right.
So the n, if we take the curl of n, we get m. N is an integer variable that you define on the square, a plaquette. Okay. So the dual. So one of the lattices. Imagine a square lattice. The dual lattice is a square lattice superimposed with a center with the sites at the center of each one of the squares. Not exactly the same lattice. In the case of the Ising model, it's self-dual, okay? And at the same temperature. This is not at the same temperature. Okay.
Thank you.
So this is a question from an experimentalist perspective. So for us, I think an important post-74 development was the finite frequency extension of Kosterlitz dualness theory.
Of course.
Could you comment on that?
Yes.
Maybe beyond
No,
Alpert?
Right. So what happened is that the KT theory is static. It's not time dependent. So, but people were doing experiments in the Andrei-Kashvili type experiments where it's a time dependent thing. So very quickly, Ambegokar, Halperin, Sija, and Nelson extended this to finite frequency regime. And so what happened is, and now you look at the IV characteristics. And the IV characteristics, you have the I gets an exponent. It's an exponent that depends on temperature. Okay? And so the nonlinear IV characteristic, and we hear about this from Love and maybe someone else here. The IV characteristics become nonlinear. And that nonlinearity, the exponent, but it's going to have a jump. And it's taking a long time to see that jump, actually, experimentally. But then you modify that in the linear response theory. In the linear response theory, yes. And it was important to do that, otherwise you could not compare to the experiments, yes.